So in the early 20th century, physicists were bamboozled because light, which we thought was a wave, started to behave in certain experiments as if it were a particle. For instance, when you shine light on a metal, the light transfers its energy to the atoms in the metal in discrete packets called quanta. But we can't just forget about properties like interference, either. So these quanta of light aren't at all like the tiny, hard spheres Newton imagined. This result, that light sometimes behaves like a particle and sometimes behaves like a wave, led to a revolutionary new physics theory called quantum mechanics. So, after all that, let's go back to the question, what is light? Well, light isn't really like anything we're used to dealing with in our everyday lives. Sometimes it behaves like a particle and other times it behaves like a wave, but it isn't exactly like either. So now we saw light is not a wave, nor a particle. It behaves as a wave and a particle at the same time. Now there arises the question for particles. Since light which we thought as a wave also behaves like a particle in photoelectric effect, does particles like atoms also behaves like wave? For answering this question we had conducted the famous double-slit experiment with atoms. If you shoot single atoms through two slits, with the detection screen on the other side, and you do this repeatedly, these single atoms do not show a pattern like individual particles would, that is two bands of particles, rather they show an interference pattern like a wave. Similar to the pattern that a wave of water would make if going through two slits. This means that the particle going through the slit is either interacting with itself, or other particles that are about to be fired but haven't gone through the slits yet. Okay, so this may be a bit weird, but most people can probably accept it that atoms behave like ocean waves, instead of like balls. But what is truly bizarre and unbelievable is that when you try to find out what's going on at the slits by placing a detector there to see what's happening with the atoms. By the way, this is called a which-way information. In other words, if you try to detect the trajectory of these atoms, then all of a sudden it will stop behaving like waves, and now behave like particles. And this can be recorded on the screen behind the slits. You might say, well, maybe the detectors are messing with the flow of atoms somehow. Maybe when photons bounce off the atoms and going to the detector that disturbed the atom and collapsed its probability wave. But if you keep the detectors there but turn them off, so that no measurement actually gets made, the screen again shows an interference pattern, and as soon as you turn the detectors back on, the interference pattern goes away. But here, we get to one of the craziest experimental results in all of physics. The interference pattern is seen even if you fire those atoms one at a time. Well, let me back up a bit. The first atom is detected as having arrived at a very particular location on the screen. The second, third, and fourth atoms, also they deliver their energy at a single spot, and so they appear to be acting like particles of well-determined position. But check it out. If you keep firing those single atoms, you start to see our interference pattern emerge once again. This is so bizarre. This pattern has nothing to do with how each atom's energy gets spread out, as was the case with the water wave. Each atom dumps all of its energy at a single point. No, the pattern emerges in the distribution of final positions of many completely unrelated atoms. How can that be? Each atom has no idea where previous atoms landed or where future atoms will land, yet each atom reaches the screen knowing which regions are the most likely landing spots, and which are the least likely. It knows the interference pattern of a pure wave that passed through both slits equally, and it chooses its landing point based on that. It turns out that the atom isn't the only thing that does this. Shoot a single photon through a pair of slits and it'll also appear to land at a single spot on the screen, but fire many photons and they slowly build up the same sort of interference pattern. This crazy effect has even been observed with electrons, even whole molecules. From these experiments and results, a well-known scientist named Louis de Broglie concluded that most particles are too heavy to observe their wave properties. When the mass of an object is very small, however, the wave properties can be detected experimentally. De Broglie predicted that the mass of an electron was small enough to exhibit the properties of both particles and waves. In 1927 this prediction was confirmed when the diffraction of electrons was observed experimentally by C.J. Davison.